Most students survive calculus without actually understanding what dy and dx actually mean. And they are being told, just memorize them. But this is such a false way to learn calculus, because dy and dx must be understood as they are the foundations of calculus. So, in this video, I will teach you to understand dy and dx in under 25 minutes. This is heavily simplified, so if you have any inquiries, let me know in the comment section and I will answer all of them. Okay, so first thing to understand is that calculus is a game of change. Okay, so in order to understand what dy and dx means, we must know that calculus revolves around change. It looks at how a function changes according to x, how fast the function changes, etc. And consequently, we have these two things, dy and dx, which are basically just means small change in y and x. So to better understand it, let's get back to the old days of where we just learned about linear graph. Okay, computing in linear graph is fairly easy. Why? Because linear graph is fairly simple, right? You just have one straight line and it doesn't change. Its steepness is constant. You can have a very flat graph or a very steep graph, but it doesn't act like a roller coaster where it goes ups and down and there's some flat point, there are very steep points. It doesn't work like that. And since they are constant, we can just pick 2 points. And these 2 points, we can calculate the difference of x and the difference of y. Difference of x being called delta x, the difference of y being called delta y. So, how do we find the steepness? Well, the steepness is called gradient, and it's delta y over delta x. Why is it delta y over delta x? Well, we must all agree to one singular point, is that the greater the gradient is, the greater the steepness is. That means the steeper the graph is. Okay, so let us actually see what will happen if we make it steeper. You might notice that delta x is decreasing while delta y has increased. And since the denominator is decreased and the numerator is increased, then naturally the gradient will get up too. Now that is all gone out of the way, let us transition into curves. So, one of the more interesting properties about curves is that it doesn't have a steepness, it varies. See, I picked 2 points, and the first point is notably flatter than the second point. The second point is much more steep. And we cannot really determine the steepness of this curve because, well, it varies. There could be some parts where it's just flat, and there could be some parts that are so steep that you cannot even climb it if you were to climb it, right? Now, what do we do instead? We can just find the steepness at a certain point. So let us bring the 2 points together, and until they are basically at one same point. So it's basically bringing them together, meaning the delta x is approaching to 0. Okay, here's the thing though. Why isn't it delta x equals to 0? Why does it have to be delta x approaching to 0? Well, here's the thing. Delta x means the change in x, right? Remember, for gradient or for steepness, we're trying to find the change. How steep it is means like how much y change compared to how much x change, right? How much y goes up and how much x goes right. That is what we're trying to find for steepness. But if x doesn't move at all, delta x equals to 0, then there's no point in finding the gradient then. There's no point in finding the gradient because if x doesn't move, y doesn't move. And if y doesn't move and x doesn't move, then what is there to calculate? What are we trying to do finding the steepness? What kind of steepness even that? However, it is important to note that in the curve, again, we cannot do it in two separate points. So delta x is not 0, but it's approaching 0. Now, as delta x approaches to 0, we cannot call it delta x and delta y anymore. This is where the terms go in. It's now called dy and dx. The main difference being delta x and delta y has a real value, while dx and dy is merely a notation of concept. So, there you go. The gradient is dy over dx. And this is what we call derivative. So by definition, this is the steepness. And that steepness teaches us the rate of change. Okay, remember, it's all about change. Now, to better understand dy and dx, let us steer away from all of the graphs for a while. The graphs we learned is all two-dimensional, which means there will be needed two variables to satisfy the graph. However, to understand it even more, let us remove the y and focus on a single variable. Let's focus on x for a while. Okay, so why do we focus on x? Because x is the independent variable, and most likely is you're going to encounter a situation where x is the part of the function. Okay, so let us square this. It becomes x squared. Now, notice how x squared is different from x, of course, but they are related. X squared is influenced by x, and x affects x squared. So let us ask ourselves a question. How does x squared change when x moves a little? This entire question can be denoted as this, which is called taking the differential out of something. In this context, taking the differential out of x squared, right? So first, how much does x squared change when x moves a little? Let us see the behavior of x squared. When x changed, x squared will change as well. When x does not change, x squared does not change. And when x changes a lot, x squared changes a lot as well. So it's clear that x squared is vastly influenced by how much x changes. And in our question previously, we are being asked if x moves a little, which remember is dx, right? X moves a little means the little change in x. So when we take the differential out of x squared, it is proportional to the little change in x, which is dx. Now, the second factor is, let us compare it actually, x squared to x cubed. Then we will watch how x squared grows compared to x cubed. Notice how x cubed grows so much faster than x squared. In the graph as well, x squared grows noticeably slower than x cubed. And that could only be caused by something. Remember this thing? It's the steepness. The steepness of the graph, which means it is proportional to how sensitive x squared is to x. Or in other words, the rate of change of x squared to x. Of course, from previously, from the graph and from the numerical example, we noticed that x cubed grows so much faster. That means x cubed has a bigger rate of change compared to x squared. And what was the rate of change? It is x squared differentiated with respect to x. Now, in this video, I am debunking misconceptions and deepening understanding. So I assume that you have at some point learned about how to differentiate something. And in this case, we will apply the power rule. So I will not be teaching it from zero because I'm trying to deepen the understanding instead of teaching something completely new. But if you want to see that, please leave a comment in the comment section. So, since when we take the differential out of x squared, it is proportional to 2x and dx, we can conclude that when we take the differential out of x squared, it is equal to 2x dx. So when we take a differential out of something, it is their derivative multiplied by the small change of that variable. Okay, if this were to be y squared, then it would be 2y dy. Understood? Okay, now how does this single variable knowledge transfer to the multivariable ones, like before? dy over dx. Now, remember what dx means? The little change in x. So dy over dx just means the ratio of the change in y to the change in x. This is not literally a fraction, but it behaves like a fraction because this is a limit of ratio of changes. Remember? Let us look at the previous graph. When we look at this, it's fair to say that they have values. So we can just find the gradient. But remember, in this context, delta x approaches to 0. So dy and dx holds no value. That's why it's a limit of ratio. It is not literally a fraction, because fraction needs to be two real values, but dy and dx aren't. But they are considered like a fraction. They are behaving like a fraction because it's simply a ratio. Now, let us take a look at this. We are naming x squared as y, so y equals to x squared. Now let us take the differential out of both of them. We will see how much y change and how much x squared change. Y changes by dy, and x squared changes by 2x dx. So the ratio would just to be 2x. This is the change in y compared to the change in x equals to 2x. Now you might be wondering, why is it 2x? Why does the ratio contain a variable? And that's a great question. But we must look back at our graph. Notice how this part is less steep than this part. So really, the gradient is influenced by which point you're calculating. So here it is. The change in y compared to the change in x. Meaning this is the limit of ratio of changes. Here's another example, but this time we'll do an inverse function. Y equals to ln of x. If you didn't know that the derivative is 1 over x, how would you solve this? First, you might know that this is an inverse of the exponential function. So let us make it e to the power of y equals to e to the power of ln of x, and e to the power of y, it stays the same, right? E to the power of ln of x becomes x. Now let us save this for later. We are now going to take the differential out of both sides, which means we are calculating the change in e to the power of y and x. E to the power of y changes by e to the power of y dy, while x changes by dx. So dy over dx equals to 1 over e to the power of y. And what was e to the power of y? It was x. So it is equal to 1 over x. Remember, it's a limit of ratio of changes. And you might be thinking, oh, because it's a ratio, then we can just switch it. Absolutely. Remember, this is an inverse function, so we can do it either way. Let's get it back to e to the power of y, and let's just switch it. Voila. No problem. But the problem is now, what you're looking at is the change of x compared to the change of y. This might be useful in some contexts, but in most textbooks you will see dy over dx, because that's what we're always looking for. But remember, the purpose of us understanding is not to find patterns on what type of questions always come out, but to truly understand it. And yes, these happen sometime. Remember, it's a limit of ratio of changes. And you might know that ratio composes. If you don't know what that means, just imagine you're trying to go to Europe, for example. You might want to know how much €1 is worth in American dollars. But you only know how much a euro is worth to pound sterling, and then pound sterling to the American dollar. How would you find the value of euro to the American dollar? Well, these are basically ratios, right? And they compose from euro to pound sterling, and then pound sterling to American dollars. So we can just take the value of the pound sterling and then multiply it by the value of the American dollar. This is the exact same process as to the chain rule. So let us take this for example. And when we are saying that u equals to 3x plus 2, we are basically telling you, hey, you are a new function inside of a previous function, which is y, right? And your job is to connect x to y. So then, okay, we can substitute this by u, and notice how there's a pattern. Y equals to u something, and then u equals to x something, which is basically like this, the cycle is, right? When x changes, then it goes to u changes consequently, and then when u changes, consequently, y changes. It's like a chain, and that is why it's called the chain rule. And because of that, we can find the change in both of them. But firstly, we must find the change in u first. Alright, the change of u becomes du, and 3x plus 2 is 3 dx. Now we'll find the change in y. So you get dy equals to 5u to the power of 4 du. Now notice how inside of the change of y there is the change of u. Inside of y there is u. This is the exact same process as before. Euros to pound sterling to American dollars. Right? So we can just change the du here with 3dx. And there you go, dy over dx. And it does look like it cancels each other out. It does look like du and du will cancel each other out, which gives us dy over dx. But the truth is, it's not really like that, but rather because of ratios composing. That's why we don't say dy over dx is literally a fraction, but they kind of behave like a fraction because, well, it's a ratio. Not really a ratio, but the limit of a ratio. Remember, when x changes, u changes. When u changes, consequently, y changes. Ultimately, y changes because of x. Now, another way we can truly understand dy over dx is by implicit differentiation. It's a form where y isn't dependent on x, and x is solely the independent variable. For example, circle equation. Here, both of them are fairly independent. They're not dependent on each other. So, what do we do here? Well, we can just take the differential out of everything. 2x dx, 2y dy, and since 1 is a constant, then it becomes 0. Move some things around, divide by 2, and then voila. dy over dx equals to negative x over y. So that is the meaning of dy and dx in differentiation. Now, you might be wondering, this oddly looks familiar, because it is familiar. Yeah, it is integral. But you might always be wondering, what does the dx mean? And why does it have to be multiplied by the function? You might only know dx as like, oh, we are integrating with respect to x. And that is true, but there's a reason why they put it this way. There's a reason why this notation works. So, let us come back to this x squared graph for a while. When we zoom in, this is just an illustration by the way. When we move x by dx, x squared moves by 2x dx. And this happens everywhere. Remember that dx is very, 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 very small, so it really happens anywhere. And everything is 2x dx. Now notice that 2x dx is like a small part of x squared, the tiny change in x squared. What if we add them all up? When we add them all up, it's x squared. So that's why the integral of 2x dx equals to x squared. Integral literally just means sum. That's why the notation kind of looks like an S. Now, here's the problem though with integrating something. Let's add 5 to the function. Yes, it's gone up 5 units, but does the behavior really change? When you add them all up, it is still x squared. The shape is still an x squared. The only problem is the height. Like when we minus it by 2, the behavior is still like an x squared graph. And when we add them all up, it's still x squared. The shape is still like x squared graph. So what does this mean? We have to add constant c, because we don't really know where the change started. And since what we sum up is the derivative of the answer, integral is always deemed as an antiderivative. Now, this process of summing is the exact reason why integral is always associated with area. Let's take y equals to x, for example. This is the graph. Let's say I want to find the area under the graph from 0 to 5. Y is the height, and x is the width. So, since y equals to 2x, the height will be 2x. Now, how can we calculate this? If we just multiplied the height by the width immediately, 2x multiplied by whatever the width is, this is 5, right? We will get a rectangle, which doesn't really represent what we're trying to look for. But what if we split it into 2 parts? More accurate, but not really that accurate. 4 parts. Okay, more accurate. 8 parts. More accurate. And eventually, until we make very, 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 very small cuts, and until they're basically the same shape. Now, remember what we learned before. dx is the small change in x. I'll give you this so that you can visualize it better. Each small width of this tiny, tiny cut is equal to dx. So, since the area is height multiplied by width, the area is 2x dx. But note that dx is just a small cut. To get the whole cut from the 0 to the 1 to the 2 to the 3 until the 5th point, we must sum them up, which means integrating from 0 to 5. And we get x squared, we put in the value to get the area 25. So here's the big misconception: integral isn't area under the curve. Area under the curve is just a side effect of integration. Even the dx stand for different things. For area, the dx means little width. The way we cut the triangles into little width, that is dx. However, integration in the context of sum to x dx just means taking the differential out of x squared. So, that is the whole explanation about dy and dx. I hope your understanding becomes much deeper after you view this video, and I hope that this video can help you excel more in your calculus class. If you have any questions and feedbacks, please leave it in the comment section. Thank you for watching, and I hope to see you next time.